Okay guys, this is Module 7, Describing Chemical Reactions. So in this module, everyone's going to learn how to predict certain types of chemical reactions. You'll learn how to figure out the products of certain chemical reactions when you were only given the reactants, and vice versa. You will figure out how to determine the reactants when you are given the products. You'll also learn how to count the atoms and molecules in a sample of matter. So while there are more, for our purposes, we're going to now focus on the three basic types of chemical reactions. And those are, number one, decomposition. And the way I think of this is, let's say you have a Lego build and you're taking it apart brick by brick, okay? Number two is formation reactions, and that's the opposite of decomposition. So that would be taking your individual Legos and forming your Lego creation, okay? And the third basic type of chemical reaction we're going to focus on are combustion reactions. And those, I think about fire. Okay, and the reason why we're starting with these is because they are fairly simple to describe, and the equations are relatively easy to predict what's going to happen and also balance. So we're going to start with decomposition. Decomposition reactions are the easiest to figure out what's going to happen with the reactants. Okay, so the reactions are the easiest to figure out what's going to happen with the reactants. So decomposition reaction is a reaction that changes a compound into its constituent elements. Okay, so you take the elements that are in a compound and it forms those elements. Okay, if any molecule contains a homonuclear diatomic element in a decomposition reaction, it's going to produce homonuclear diatomics as products, okay? And we'll go into this a little bit more in just a minute. So in your book on page 242, this right here, figure 7.1, shows the decomposition of water. So what's happening in this figure? All right, so right here you can see that there's a battery and it's in a solution of water and baking soda. There are two test tubes, one here and one here, and they're over the battery posts. One's on the positive end and one is on the negative end. So the oxygen gas has bubbled up and formed over the positive post, and as it fills up this left test tube, it pushes the liquid down and out of the tube, okay? And same thing, similarly over here, hydrogen gas bubbles form on the negative post and fill up that test tube, pushing the liquid down and out of the tube. You can see that there's about 2 times the amount of hydrogen gas produced than oxygen here, okay? Right here is the amount of oxygen, right here is the amount of hydrogen. So water produces hydrogen gas and oxygen gas, okay? Let me move this up right here. This is the decomposition reaction for water, all right? You have 2 water molecules that are liquid, and it produces 2 hydrogen and 1 oxygen. Now remember, hydrogen and oxygen are both homonuclear diatomics, and so that's why they're listed here as H2 and O2. So you are going to need to remember those, okay? ATBRINCLHOF. All right, so make sure that you remember those for moving forward. So remember that compose means assemble. So in these, in the decomposition, decompose means to break apart. So that's what we're looking at, water splitting into the individual elements. So the trick is to make sure in these that you're giving 2 atoms to all your homonuclear diatomics, all right? So now let's move on to example 7.1 on page 243. All right, so example 7.1, let's work through that together. It says, write the chemical equation that describes the decomposition of ethanol, and it gives you that C2H6O. So that's what we're going to start with. So ethanol. We know that it's a decomposition reaction, so the products are going to be the individual elements. Okay, so this is going to break into carbon, hydrogen, and oxygen. So the first thing you need to do is to determine which are homonuclear diatomic, and that would be hydrogen and oxygen. So it's going to produce carbon, and it's going to produce hydrogen, and you need to give it 2 atoms, and it's going to produce oxygen. Okay, so the next thing you need to do is balance this equation. Your book works through some different methods on how to do this. It really doesn't matter which way you go with it, as long as your answer, your final product, is the correct answer. So if you want to use fractions, which is one way your book suggests doing it, that's fine. I personally don't use fractions because I don't need to, but it's not a problem too. So the first thing I look at is what I have. I have 2 carbons here, 1 carbon here, 6 hydrogens here, 2 hydrogens here, 1 oxygen here, and 2 oxygens here. So I automatically know that there's gonna need to be a 2 here because there's 2 oxygen here and only 1 here. So that's where I start. So once I give this a 2, it gives me 4 carbons. So I need a 4 here, and it's gonna give me 12 hydrogens. So I'm gonna need a 6 here. And then I check to make sure that everything is balanced on each side, my reactants and my products. And so here I have 2 times 2 is 4, and I have 4, so the carbon balance is 2 times 6 is 12, and 6 times 2 is 12, so my hydrogen balance is. Here I have 2 times 1 is 2 for oxygen, and 1 times 2 here is 2 for oxygen, so everything balance, okay? So the final answer of your balanced equation is always going to be the same, but there might be more than one way to get there. So maybe you didn't start with this molecule. Maybe you started over here and you gave your hydrogen 3, and then you quickly found out. If you're trying to balance the equation and you're having issues, go back to the beginning and start with a different element, okay? That will help you. Hopefully this makes sense of what I'm doing. So we're going to be doing this moving forward. So scan over the equation, determine which atom to start with for balancing, and that's kind of how I do it. All right, so I want to work another example with you. This one says, write the balanced chemical equation for the decomposition of SiH3F. So you know that this is going to decompose into the individual elements. And it's going to break down into silicone, which is not diatomic. It's not a homonuclear diatomic. Hydrogen, yes it is. Make sure to put your 2 atoms. And fluorine, yes it is. Okay, so now I have to balance it. All right, so I look at my equation, I see what's going on. I have 3 hydrogen, I have 1 silicone, 1 fluorine. Over here I have 1 silicone, 2 hydrogen. So I can right away tell that hydrogen is kind of the issue. So that's where I start. I'm gonna need multiples. So I put a 3 here, which gives me 6. And if I do that, I'm gonna have to put a 2 here to match and give me 6 hydrogen. And I go from there. So then I have 2 silicone. And then right here, I have 2 fluorine, 2 fluorine. Everything matches up. Silicone on both sides, 2, 2, check. Hydrogens on both sides, 6, 6, check. Fluorines on both sides, 2, 2, check. So I did this correct, okay? So most chemists consider any reaction with a single reactant and more than one product as a decomposition reaction, okay? It doesn't necessarily need to break apart all the way into its individual elements, but this is how we're defining this for this class. I just want you guys to know that that's a little bit of a narrow definition. So for us, we will be breaking them down into the individual elements. But let me show you. Calcium carbonate. So that would be an example. All right, so now let's move on to formation reactions. Okay, so remember that formation reactions are pretty much the opposite of your decomposition reactions. It's the inverse, right? It would be taking the Legos and making the creation. So elements are composing to form your substance. So formation reaction is a reaction that starts with 2 or more elements and produces one compound. So it can be an element plus an element, and it can be another element. It just has to be 2 or more. And it produces your compound. Okay, so if we look at the formation of water, starts with hydrogen gas, oxygen gas, and it forms water molecules. Now remember, hydrogen and oxygen are homonuclear diatomic, so they need to have 2 atoms here. Okay, so now we're going to balance it. So here I have 2 hydrogens, here I have 2 hydrogens, here I have 2 oxygens. I don't, so I need to have 2 over here, which will give me 2 oxygens. That's good. And I need 4 hydrogens, so I'm going to have to put a 2 here, and then everything is balanced. Okay. So again, this is a little bit of a narrow definition, but for this course, only elements will be reactants in our formation reactions. Okay, so let's do example 7.2. Write the chemical equation for the formation of magnesium carbonate. Okay, so we know what the individual, we're going to have magnesium, we're going to have carbon, and we're going to have oxygen, right? We know that from right there. Now, are any of these homonuclear diatomics? Yes, oxygen. So it needs to have 2 atoms there. And then we're going to produce our substance, magnesium carbonate. And then now you need to balance your equation, okay? So again, I look at I've done enough of these, but hopefully after you guys practice, they'll make sense to you. It'll be easier and easier. But the first thing I notice is that there's 2 oxygen and 3 oxygen. So I've got to make those even. So I put a 2 here, which will give me 6 oxygen. And then if I put a 3 here, my oxygens are going to balance. And then I look at everything else. So I have 2 magnesiums. I need 2 magnesium. I have 2 carbons. I need 2 carbons. And that is my balanced equation. 2 magnesiums, 2 carbons, and 6 and 6. I hope that makes sense and that gets easier as we go along. And now we're going to move on to combustion reactions. All right, so now we're moving on to talking about combustion reactions. So what do you think about when you hear the word combustion? Well, usually people think about something burning or blowing up. When candles burn, they release heat and light from the flame. Some combustion reactions in chemistry don't release heat or light. So for chemistry, we define combustion reactions as a chemical reaction where a substance reacts with oxygen gas. So again, for chemistry, we define combustion reaction as a chemical reaction where a substance reacts with oxygen. So what I want you to think about is a candle. A candle needs a constant supply of oxygen to burn. So I'm gonna light this candle right here for you. Okay. What happens if I place a glass over my burning candle? Let me show you it's still. And now it's out. All right. So what happened? Sorry, I'm trying to balance this for you. What happened to our candle? Well, the flame went out. When did it go out? Did it go out the second I put the glass on it? No. It went out after it used up all the remaining oxygen trapped inside of the glass. Because in order to keep burning, that flame needs oxygen. Okay? There are types of combustion reactions that do not involve oxygen, but in this class, in our course, that's what you're going to focus on, okay? The ones that do. So in general, move this out of the way. You're going to have a reactant plus oxygen, and it will give you a product for combustion reactions. Okay, so if oxygen can be classified as a reactant in the reaction, it can be classified as a combustion reaction. Now there are different types of combustion reactions. We're going to look at 3 of them. There's combustion of metals, there's complete combustion, and the third type would be incomplete combustion. All right, so we're going to talk about combustion of metals. So this is talking about metals burning in the presence of oxygen, and this is what happens with fireworks, okay? So the following reaction, you have magnesium with oxygen, and it reacts to make magnesium oxide, okay? This releases a lot of heat and it produces a very bright white light. Fireworks used to be made with magnesium a long time ago. Now they're not usually anymore because this reaction, it produces a lot of heat and it could be injury prone if someone were to touch it after an extended period of time. But lots of different metals can react and produce different combinations of light, which is what you'll see. Sodium creates a yellow light, potassium creates a pale purple light. So that's important to know. Combustion reactions have to have oxygen gas as a reactant, but they don't always have to release heat and light. And we'll talk about this in a minute, but when iron rusts, it does not release light. It does release heat minimally. It's very hard to detect, and it reacts with the oxygen slow that our eyes can't really see it. So it's worth mentioning. But okay, now we're going to move into complete combustion reactions. So a combustion reaction is one where oxygen gas chemically reacts in the burning of a substance, okay? Most combustion reactions begin with a compound that contains carbon and hydrogen, producing carbon dioxide and water. So this is for complete combustion reactions. You're going to have, okay, I guess I have this right up here, right? That's for combustion. Now for complete, you're going to have some substance that has carbon and hydrogen plus your oxygen, and it's going to produce carbon dioxide and water. Okay, when these products are formed, you have a complete combustion reaction. Okay, so again, that's a reaction in which oxygen is added to a compound containing both carbon and hydrogen, which produces carbon dioxide and water. Let's look at an example. Remember, oxygen is homonuclear diatomic. In this reaction, again, if you're wondering why this is a gas, it's because so much heat is released. Okay, so I just wanted to show you. Now we're gonna look at example in our book 7.3, which is right here. A butane pocket lighter works by evaporating and then burning the liquid, oh, that should be butane, sorry about that. The liquid butane, C4H10, stored in it. These are those old lighters. I don't know if you guys have ever seen them, but write the balanced chemical equation for this complete combustion reaction. All right, so it gives you butane. It tells you it's a complete combustion reaction, so you know that that means oxygen is involved, and also gas. You actually know that this is a gas. Why do you know that this is a gas? Because it tells you it's a liquid, but it says it works by evaporating and then burning. So you know that that's got to be in its gas state. Okay. And complete combustion is going to produce carbon dioxide and water. And again, this is because of all the heat that's released. Okay, so now you just need to balance it. All right, again, your book walks you through how to do fractions. Again, I'm just gonna show you my method. I use whole numbers, it works for me. If you start balancing your equation and you mess up and you can't do it, start over. Start with a different, if you started with oxygen and you got hung up, start over, start with carbon, see if that helps you. Or if you started with carbon, then start with oxygen. As you do more and more, you'll get better and better at figuring these out, okay? So the first thing I do is I look at my carbon and I have 4 over here, I have 1 over here. I have 10 hydrogen over here. I have 2 over here. And then I have 2 oxygen and I have 3 oxygen. So these are kind of where I start personally. I know that my oxygen, I probably do that second, just by looking at it. So what I do is I'm going to start, I know that I'm going to need to have a number here because of the way that my oxygen is set up. So I start with a 2. That's just how I do it. Again, I've done enough of these. So I'm going to start with my carbon. So I've got 8 carbon here now. Now the reason why I didn't just leave it and start with a 4 here is because I can just tell that that's not going to work with my oxygen. But if you wanted to start there, that's totally fine. I'm just saving time here. So I start with a 2 here, and that's going to give me 8 carbon. So then I put an 8 here for carbon, and everything looks good. Well, right here, that's going to make me have 20 hydrogen. I only have 1 place for hydrogen over here, so that's going to make that a 10. And then all I have left is my oxygen, which is why I started the way I did. And this produces 8 times 2 is 16. Plus 10 is going to give me 26 oxygen. And then I put a 13 here and everything should balance. Carbon on this side is 4. Carbon on this side is 8. I said 4. Carbon on this side is 8. Hydrogen on this side is 20. Hydrogen on this side is 20. And then oxygen is 26, and oxygen over here is 16 plus 10, which is 26, and so everything balances. So that is the balanced chemical equation for this complete combustion reaction, and I hope that makes sense to you. Now let's move on to incomplete combustion reactions. All right, so now we're moving on to incomplete combustion reactions. So remember that in order for things to burn, they need lots of oxygen. Think of the candle that I just showed you with the glass over it and what happens when the oxygen is taken away. So combustion needs a constant supply of oxygen to burn. Well, what if something doesn't have enough oxygen to completely burn up? If there's a limited amount of oxygen, a substance made of carbon and hydrogen will not burn completely. This will undergo an incomplete combustion reaction. Okay, now for incomplete combustion reaction, carbon dioxide is not one of the products that will form in an incomplete. Instead, it will either be carbon monoxide, CO, or it will be just carbon. Okay? So let me give you 2 examples. If I have methane or natural gas, and I have oxygen, I've already got these kind of written out. Or methane, natural gas. I can get carbon. Okay, so here's 2 incomplete combustion reactions that can happen with methane and oxygen. Which one occurs depends on the amount of oxygen available in the area where the reaction is occurring. If there's a fair amount of oxygen, it will yield this first incomplete combustion reaction. Okay? If there's more limited oxygen, we'll get the second one. When we get a carbon product equation, the product is often called soot. This right here. Okay, this is soot. And it can be found on the inside of fireplaces. So complete combustion reactions produce carbon dioxide, while incomplete combustion reactions produce carbon monoxide, which is a poisonous gas, or soot. Okay, so carbon monoxide, this is part of what occurs with car engines. You've probably heard to never start a car or never run a car in a garage with the door closed. This is why. Because it would produce carbon monoxide, and it would not have a proper ventilation, and that's a poisonous gas. Carbon monoxide is odorless, and it's clear, so you don't really know that it's happening. And also for cars, in 1975, the U.S. passed laws for cars to have catalytic converters installed. These devices in the car help reduce how much carbon monoxide is released in the car exhaust. And the way they do that is by taking carbon monoxide and converting it to carbon dioxide. It doesn't eliminate the problem. It doesn't do it completely, but it does reduce it. So that is something worth noting. In cold temperatures, natural gas furnaces have to burn gas faster than the oxygen supply can be taken in. Then carbon monoxide will be produced. Okay. Now, a lot of that will flow out of the house, through chimneys. But if there's not good ventilation, some can remain in the house, and that's an issue. So same thing with fires and fireplaces. They can produce carbon monoxide. That's why there always needs to be a really good airflow at the base of the fire to avoid it, the oxygen supply. And the amount of soot that you find in a fireplace can be a good indicator of how well or how poorly your airflow is, right? So a lot of soot happening means both types of incomplete combustion reactions are occurring. And like I said before, carbon monoxide has no color, no odor, so you really need to have good ventilation to get rid of it. So I know that many of you are probably not necessarily going into chemistry, or maybe you don't desire to be a chemist, but this is just an example of how chemistry can be super important. This is a way it just shows you safety, so it's worth mentioning. All right, so now we're going to move on to atomic mass. All right, so now we're moving on to the atomic mass. So we're going to be talking about counting atoms and molecules. So you can measure the mass of a sample and then figure out what types of atoms or molecules are in the sample. Then you can determine how many atoms or molecules there are. Okay, so moving back to the periodic table, I'm going to do like a little bit of a refresher. So this is hydrogen. This one up here, these numbers up top, okay, that is your atomic number. We've learned about this before. Remember, that tells you how many protons the atom has in its nucleus. Okay, then you've got right here your atomic symbol. So for hydrogen, the atomic symbol is H. And then down here on the bottom, I don't know why I typed it in wrong, but I'm sorry. It is 1.01, and you can see that right there. It's that number on the bottom. And that is the atomic mass. It tells us how heavy the atom is. So what are the units going to be for atomic mass? Well, they're going to be AMU, which stands for atomic mass units. I know, super exciting. Okay, so 1 AMU, I need paper. Let me move this. All right. So 1.00 AMU equals 1.66 times 10 to the negative 24 grams. You will be given this information when it is needed on problems, okay? So nope, you do not have to memorize that. You will be given it. Now remember, 1 gram, what weighs about a gram? Remember your book said a housefly, and we talked about a paper clip, a dollar bill. So 1 AMU is 1.66 times 10 to the negative 24th. This shows you how tiny AMUs are, okay? So now we're gonna look at example 7.4 together. It says, what is the mass of 1 nitrogen atom in grams? And it says, remember, 1.00 AMU equal 1.66 times 10 to the negative 24th grams. So we're dealing with nitrogen. So you find it on the periodic table. Here it is. And the atomic mass right there, 14.0. So we just set up our equation, 14.0 AMU. Nitrogen. 1.00 AMU nitrogen is 1.66 times 10 to the negative 24th grams nitrogen. And our units cancel out. And that is going to give us 2.3. Okay, so this is a conversion that should look familiar to what we've been working on in the past. So let's move on to molecular mass. So after determining the mass of atoms, you can now figure out the mass of molecules. Well, how do you do that? You just add up the masses of the atoms that make up the molecule, okay? So example 7.5, what is the molecular mass of CHCl3 in AMU? Okay, so let's do mass of Okay, so carbon, I have 1 of those, and it's going to be 12.0. Let's do carbon, hydrogen, really quick. So carbon right here is 12.0, right? Hydrogen, we just did a minute ago, 1.01. And then chlorine right here, 35.5. That is where these numbers are coming from. So that should make sense to you. Hydrogen, there's 1. And there's 3 chlorines. Oops. Sorry. 3 times 35.5 AMU. So we're adding this up. We're adding this one, adding this one, adding this one, adding this one again, adding this one again. I'm just multiplying it by 3 just to save time, okay? So really this is not multiplying, it's really adding, right? We're adding this mass, adding this mass, adding this mass, adding this mass, adding this mass. So when it comes to significant figures, this is important because you're gonna follow the adding and subtracting rules for significant figures, which is to keep the lowest precision, okay? So remember that. This is precise to the tenths place, to the hundredths place, to the tenths place. So our answer is going to be to the tenths place. Okay, so we add all these up, and the mass is going to be, and then we know this is to the tenths place, so we're good with significant figures. Hopefully this makes sense for this problem. Let's do another example. What is the mass in grams of lithium carbonate molecule? And let's say that's what they ask you. You should be able to determine this because you are supposed to know what carbonate is, okay? So lithium, if you look on your periodic table, it is over here in group 1A, so it has a +1 charge. And carbonate, you know, CO3, and it has a -2 charge. So lithium carbonate is going to be, reverse your subscripts, and you're going to get 2, and then you don't need to put a 1 there. Okay, so you're going to follow the same thing. What's the mass? Well, there's 2 lithiums. There's 1 carbon, and there's 3 oxygens. Lithium is 6.94 right there. Carbon is 12.0 right there. And oxygen is 16.0. AMU, 12.0 AMU. So you multiply and add these all up, and you get 73.9. And this is correct because the least precise is to the 10th place. But now I have to do my conversion because it asked for it in grams. So take my 73.9 AMU. And remember, this will be given if you need it. Your 1 to 1.66 times 10 to the -24th. And my answer is going to be 1.23 times 10 to the -22nd grams. And this is correct. It needs to be 3 significant figures because when you were adding, it was to the precision. And then down here in this problem, it's going to be the significant figures, okay? So that would be the answer to this problem. Now we're going to move on to talking about moles. I had mentioned this before and no one really knew what I was talking about. So we're going to jump into that next. All right, guys. So now we're moving on to the mole concept. So you all know that the word dozen refers to a group of 12 of something, right? So if I were to tell you I have a dozen eggs, you would know automatically I have 12 eggs. If I told you I had a dozen children, you would know right away I had 12 children. Well, chemists have a group term for a specific quantity of atoms. And this group term is called a mole. Now this number has to be a really big number because you're not going to be able to do much if you had a dozen atoms, right? So a mole is 6.02 times 10 to the 23rd of something, okay? And this is also referred to as Avogadro's number because the chemist who helped lead to the discovery. Now, Avogadro's number tells you how many atoms are in a sample of an element when the sample has the same mass in grams as the element's mass in AMU, okay? So we're gonna do some different examples and work through this. Okay, so the mass of a carbon atom is 12.0 AMUs. If I go right here to carbon, I can see 12.0, right? Okay, so what this is telling you is that if you have a 12.0 gram carbon sample, it's going to contain 6.02 times 10 to the 23rd atoms. That is what this is telling you, okay? Likewise, if you looked at another one, let's say sulfur, right here, 32.1. So the mass of a sulfur atom (32.1 AMU). So if you were to have a 32.1 gram sample or grams of sulfur, it's going to contain 6.02 times 10 to the 23rd atoms. I hope you see how this is relative. Even though these samples contain the same number of atoms, they're completely different. It has to match up with the mass, the element's mass in AMUs in order for that to be the case. So 4.0 grams of helium would contain 6.02 times 10 to the 23rd atoms. 55.8 grams of iron would contain 6.02 times 10 to the 23rd atoms. Okay, hoping that makes sense to you. And then 1 mole of atoms equals 6.02 times 10 to the 23rd. All right, so let's look at something slightly more complicated. What about water? Okay, so my atomic mass for water remember, I have 2 hydrogens. It's really like adding 1.01 plus 1.01. And my oxygen plus EMUs. So for water, okay, remember when I'm adding, I need to go to the one with the least precision, which is going to be the 10th place. Okay, so if I have 18.0 grams of water in that sample, I have 6.02 times 10 to the 23rd molecules water in that sample. Or 1 mole of molecules. Okay, because we know 1 mole equals 6.02 times 10 to the 23rd. So in these problems, be really careful. Pay attention to what the question asks for so you know what unit to put the atomic mass in. Okay, the atomic mass in AMU will give the mass of 1 atom. The atomic mass in grams will give the mass of 1 mole of that atom. A molecule's mass in AMU will give the mass of one molecule, and a molecule's mass in grams will give the mass of 1 mole of that molecule. That's really important, so I'm going to say it one more time. So the atomic mass in AMU will give the mass of 1 atom. The atomic mass in grams will give the mass of 1 mole of that atom. We just talked about that. Then a molecule's mass in AMU will give the mass of 1 molecule, same concept. And a molecule's mass in grams will give the mass of 1 mole of that molecule. Okay? So 1 atom of boron is 10.8 AMUs. Let's find boron. Right here on the periodic table, 10.8. So 10.8 grams of boron is 1 mole of boron. Okay? 1 atom of copper is 63.5 AMUs. So therefore 63.5 grams of copper is 1 mole of copper atoms. All right, so let's move these. Let's do this problem. How many moles of fluorine atoms exist in a 50.0 gram sample of fluorine? So what is it asking me? So in a gram of fluorine, wants to know how many moles of fluorine exist. So if I look at fluorine, right here, I can see 19.0. So 19.0 grams of fluorine, I'm going to write it this way, equals 1 mole of fluorine, right? We just talked about that. So now we just do our conversion. How many moles of fluorine atoms exist in a 50.0 gram sample? Okay, well, I have 50.0 grams fluorine. Well, I now know that 19.0 grams of fluorine equal 1 mole. I cancel out my units. Sorry, I made that super long. And I should get 2.63 moles of fluorine. Okay, so my significant figures here should be 3 significant figures. Now you might be saying, well, why isn't it 1 because of the 1 here? That's an exact integer, not a measured amount. So that's not relative to the significant figures. So this right here lines up, and that's correct. All right, let's work through another example. All right, we're going to work through this next problem. It says people are encouraged to limit their table salt, which is NaCl, sodium chloride, intake to 5.000 grams per day. How many moles of sodium chloride is that? So the way I set this up is how I did the other one. Say so many grams sodium chloride equals how many moles? So that's the information. Okay. So to get sodium chloride, we need to get the atomic mass. So sodium right here is 23.0, and chloride way over on this other side is 35.5, if you're wondering where these numbers are coming from. Okay. So I have 1 times 23.0 AMU plus 1, there's just 1 atom in each, 35.5 AMU. So I get 50 8.5 AMU for sodium chloride. All right, so in 58.5 excuse me, grams of sodium chloride, that equals 1 mole. So now I can do the problem. It gives me 5.000 grams sodium chloride. I know that in 58.5 grams sodium chloride, there's 1 mole sodium chloride. Grams are going to cancel out, and that is going to leave me with 0.0855 moles sodium chloride. I'm a step further. So we have this exact same problem, and now let's say that they ask you, now how many molecules of sodium chloride are in that exact same sample? Okay. So we already know that this is how many moles there are. We just calculated that out. And we know that in 1 mole, there's 6.02 times 10 to the 23rd molecules. And that is going to give us our answer. 1 mole. And 1 mole, even 1 mole of sodium chloride. Okay, so that's going to give you, I think hopefully when you calculate it out, it's going to give you 5.15 times 10 to the 22nd molecules sodium chloride. Atomic mass in AMUs will give you the mass of a single atom. Atomic mass in grams will give the mass of 1 mole of that atom. And the same thing for molecules. All right, so let's move on from here. Okay, so for time's sake, I am not going to do experiment 7.1, but I do want you to read it and be aware of it. It's pretty interesting to think how we can measure out and find out information on things that we can't see. I think that's super interesting. But if you have any specific questions relating to this experiment, please reach out. Ask me if there's something you don't understand about it. You can text me, you can email, all of those things. But we are going to move on from there, and we're going to work out another problem right here. Let's see if I can try to have some of these written out for you. All right. A chemist determines that a sample of pure ammonia, which is NH3, contains 12.331 moles of NH3. What is the mass of that sample? So 12.331 moles. And I want to know the mass of the sample. Okay, so I'm going to get the atomic mass of NH3. Nitrogen is 14.0 AMUs on the periodic table. And I have 3 hydrogen at 1.01. So it's going to give me 17.0 AMU. All right. So 17.0 grams of NH3 equals 1 mole of NH3. And this is what I'm going to need for this problem. So it tells me a sample, 12.331 moles, NH3, and then you just set your problem up. 1 mole NH3 is going to give me 17.0 grams. I'm going to be left with 2.10 times 10 to the second grams of NH3. Okay, why is it 3 significant figures when there's a whole bunch more here? And it has to do right here. There are 3 significant figures and 3 significant figures, and that's why this should be 3 significant figures. So, move it on from there. All right, so now we're going to start using the mole concept and chemical equations. So I want you to think of chemical equations like recipes, right? We've talked about this kind of all year in different ways. So if you look at the coefficients, they tell you how much reactants are used to make the products, right? So in this specific reaction, we know 1 is needed here, 2 is needed here, 1 is needed here, and 2 is needed here. Okay, well, just like recipes, you can double it, right? So that's what I'm showing you right here. If we were to double this recipe of this equation, this 1 would become a 2, 2 would become a 4, 1 would become a 2, and 2 would become a 4. Well, you can also think of it, what if I said I wanted to do a dozen, right? But instead of writing out 12 and doubling at 24, I just use the word dozen, my group term. So I can have 1 dozen, 2 dozen, 1 dozen, 2 dozen. Well, where am I going with this? Well, the same concept can be applied with moles. I can have 1 mole, 2 moles. This would be 1 mole, and this would be 2 moles. Okay, so in chemical equations, know that the coefficients of each substance gives the ratio of the substances that are used in that equation. Okay, as long as the equation is balanced, you know the recipe for that chemical equation to happen. Okay, and you can do the same thing with molecules. 1 group of molecules plus 2 group of molecules of oxygen will give you 1 group of molecules of CO2 plus 2 group of molecules of H2O. Okay, so let's look at the decomposition of hydrogen and peroxide into water and oxygen. Okay, so this problem says the decomposition of hydrogen peroxide into water and oxygen is described by the following equation. So I have 2 H2O2 liquid, that's your hydrogen peroxide, and it decomposes into water, 2 H2O liquid, plus oxygen gas. If the chemist begins with 2.4 moles of H2O, which is measured in amount and will be used for significant figures, how many moles of oxygen will be produced? Okay, well, in my problem, I can see that 2 moles of hydrogen peroxide equals 1 mole of oxygen. That's my recipe. So for every 2 moles of hydrogen peroxide, I'm going to get 1 mole of oxygen. So if I start with 2.4, the chemist starts with 2.4 moles of water. Oh, actually, I'm sorry, this is supposed to be hydrogen peroxide. 2.4 moles of hydrogen peroxide. Okay, well, for every 2 moles of hydrogen peroxide, I get 1 mole of oxygen. And that's just going to give me 1.2 moles of oxygen. I hope you can see how easy that is when you use the recipe. And why is it 2 sig figs? We talked about that a second ago, but 2.4. All right, so let's do another one. If a chemist has 0.234 moles of C2H6O, how many moles of carbon will she get by decomposing the sample? Okay, so we need to do that. We start with C2H6O. We know that it's a decomposition reaction, so we know it's going to compose into carbon, hydrogen, and oxygen. We also know that hydrogen is a homonuclear diatomic as well as oxygen. Okay, so now I'm going to balance my equation. I have 2 carbons, 6, and 1. So I'm going to, okay, I'm definitely going to need to change this. I'm going to have to put, okay, because I have 2 here in oxygen, I know I'm definitely going to have 2. So that's what I start with. So once I do this, my oxygen's balanced, and then I can mess with my other 2. So that's going to give me 4 carbon, 4, and that's going to give me 12 hydrogen. And so I put a 6 there, and then I double check to make sure everything's balanced. I have 4 carbon, 4 carbon. I have 12 hydrogen. I have 2 oxygen, 2 oxygen. Okay, if you're having trouble with that, please go back and practice balancing equations. Okay, so this is my recipe. So 2 moles of C2H60 equals 4 moles of carbon, right? 2 for 4. Okay, in my sample, 0.234 moles of C2H60 and 2 moles C2H60. I have 4 moles of carbon. It's going to cancel out, and that is going to equal 0.468 moles of carbon, 3,6. Okay, so the best way is just practice on these. And I'll be right back with an announcement for you guys. Okay, so hopefully you have read the entire Module 7. You've watched this video. You've done the on your own problems, and you have a good idea of what's going to be expected. I also wanted you to know that there's a quiz on the website. It's under the resource section, not under the assignments. But there is a quiz 3. Remember, this is optional, but I highly recommend that you take it. As well, there's an extra credit assignment. Looks like this. It just says new element. While you were digging in your backyard, you discovered a new element. Tell me everything about it, okay? This is just an easy way to get some extra points if that's something you're looking for. Let me know if you guys have any questions. You have 1 week from today to get everything into me. If you haven't turned in your test 6, please get that to me ASAP. But next week and 1 week, you will have due test 7. The lab write-up that you've been working on, there will be no redos on this. You guys have had ample time to put in quality work for me. And the quiz, if you choose to do so, and the extra credit if you choose to do so. And then you'll be done for the break. I'm going to work on our syllabus for the spring, and I'll be sending it out in just a bit. Not right away, but in enough time for you to start working before we come back. We might be doing 1 module, hit the ground running, so I need to work that out. But as always, please email, text. If you have any questions, let me know. And good luck. It's a lot of material, but you guys can do it.